took a look at our homework last night as part of a review here this morning, page 553. We had 1 to 9, but we got a bunch of them that we got to go over here. That's okay. Question number 1, starting off with, says, what's the difference between an electric force and an electric field? And I think it was Jack yesterday, was it, that we're, no? Aiden? Okay. Aiden was kind of pushing like this yesterday. Aiden was the producer, right? Okay. But if I wasn't standing there to experience it, then we didn't have any force, right? In order to have a push, in order for Aiden to push something, you need to have an experiencer, right? You need to have something to be pushed. So in order to have a force, you need to have an experiencer, something to feel that force. Now, Aiden was there. Okay? Aiden's the producer. Aiden caused the influence, right? He's doing this pushing motion. It's just not affecting anything unless there's something there to experience it. The field is there as long as Aiden's there. The force is only there if I'm there to experience it. So a field is this influence that surrounds an electric charge, whether or not there's something there to feel it. A force is this push or a pull on an experiencer in that field. In other words, to have a field, all you need is a producer. To have a force, you need a producer, of course, to make the field, but you also need an experiencer to feel the field, to experience the field. You need something to be pushed or pulled, right? Number 2, why was it necessary to introduce field theory? Talked about this real briefly. In the end, it comes down to, we talked about field theory as being this artificial construct. It's a man-made or a human-made idea, this idea of fields. The idea that, let's go back to gravity for a second, because we can see that a little bit easier, right, than we can see electric fields, right? We can visualize it a little bit more. It's within our realm of experience a little bit more. And the ideas usually translate to electric fields as well. The Earth produces a gravitational field. The Earth, if something's there to experience that field, will also produce a force on that something. So if I've got the board marker in my hand right now, there's a force of gravity acting on the board marker as a result of the Earth. Force is there, as long as the board marker is there. But if I take the board marker away, there's no force anymore. So how do we quantify the Earth and what the Earth does if there's nothing there to experience it? Well, we invent the idea of fields, this concept of fields, this influence that's not influencing anything, this sphere or lines of influence that have the potential to do something. Right? If I put another board marker in the Earth's gravitational field, or a calculator in the Earth's gravitational field, or a person in the Earth's gravitational field, it will be affected. Well, we can't say that the force, how do I say this? We can't say that the influence is dependent on what we put there. Right? If I put the board marker there, there's a force. If I put the calculator there, there's a force. If I don't put it there, there's no force. Well, there has to be something there in order for the board marker, in order for the calculator to be influenced. We introduce or we invent the idea of fields to explain the idea that there's something there even when there's not something there to be influenced, even when there's not something there to experience that push or a pull. Does that make sense? Well, we talk about that with gravity, but same analysis applies to electric fields as well. The idea that, look, there's an influence surrounding charges too. But how do you quantify that if there's nothing there to experience it? Well, introduce the idea of fields to quantify it. All right, number 5. If vector arrows can represent an electric field at a point surrounding a charge, identify 2 ways that the vector arrows shown below represent differences in the electric fields around the 2 source charges. So here's one of them, and here's the other one. It's funny sometimes we see a question like this where the answer is almost staring us in the face, but we miss it sometimes because it's almost staring us in the face, and we're looking for something that's too complicated, looking for something that's harder than is the answer here. What are the 2 differences here between these 2 electric fields? Electric field, we'll call it blue electric field, we'll call it red electric field. What's one of them? Okay, so the direction is different. Okay. Not only is the direction different in terms of, look, we got one on the x-axis and one is about maybe, I don't know what 45, Rucker, maybe 40. It doesn't matter. It's at an angle anyways. There are different directions. Not only are they, one at 0, one at 45 degrees or 40 degrees, whatever the case may be, but one is toward the producer, one is away from the producer. So the direction is different. What else is different about this electric field, this vector field that we call an electric field? The producers are different charge, yes. Although it does say, what's the difference in the fields, not the producers, right? Give me another difference between the two fields that we have. In these electric fields, these examples of vector fields. The direction is different. What else is different? Why would you say that? Why is the negative field stronger there? Okay, well, take a look at that. Take a look at the length of that one. Take a look at the length of this one. Yeah, I think you'd agree that this one is longer, right? If the field is drawn as a longer vector, then what does it tell us about the magnitude? We're supposed to try to draw them to scale, right? So it's higher magnitude, right? The bigger the vector, the bigger the value of the electric field. So let's go back to the question again. What are the two differences in these two vector fields? Well, one difference is magnitude, one difference is direction, right? Which is what defines a vector in the first place. Look at that, halfway done already. 6, good question here. 6 says, describe the effect on the electric field at a point if the magnitude of the charge producing the field is halved. Well, this is a variable value changing question, right? We're going to say, for question A, the electric field is KQ over R squared. This is my original electric field. Now, my new electric field, after I make my changes to it, is K times, well, we're cutting in half the magnitude of the charge. So it's 1/2 Q over R squared. Becomes 1/2 of KQ over R squared. And of course, the value of KQ over R squared is my original field. So it's 1/2 of my original field. Okay, any problems with that one? Well, that's the way we'd expect to do this question, right? We see this, we're manipulating the value of a variable without knowing what the value was to begin with. It's going to be a variable value changing question. So that's exactly what we did. What about when the sign of the charge producing the field is changed? Well, that's not going to change the magnitude of the field, right? When we change the sign of the producer, all that's going to do is change the direction of the field. So the field is going to be in the opposite direction. Okay, so far not so bad. That's why Brad got A and B, right? Had a little bit of trouble with C though. If the magnitude of the test charge in the field is halved. Well, how many people think they got this question? Ish says. What does that mean? You're in the right order of magnitude? Okay. Okay. Let's take a look at how I think we look at this question and we want to tackle it. Okay, we see this as a magnitude of the test charge in the field is halved, so we're going to use the experiencer equation. Don't write this down yet, okay? The magnitude of the experiencer, or the test charge, is cut in half. So we're going to say E is equal to F over Q, right? That's my original field. My new field is F over 1/2 Q, which becomes 2 F over Q. And of course, that's my original field, right? So we get twice the original field, right? How many people got that? Rucker, you said ish, but you didn't put up your hand for that. Did you get that? What'd you get? Oh, Rucker did get it. This is the wrong answer, and that's why I said don't write this down. Why is this wrong? Why is this incorrect? It looks like everything I've done here, according to the analysis that we've learned on variable value changing, is exactly what I've done here. Right? It looks like what I've done is correct. E is equal to F over Q, relevant equation, right? Cut the charge in half, right? Yeah, okay, 2. I don't know, everything looks right. Rucker, what's wrong? You're saying that the field doesn't change. Why? Why'd you say the field doesn't change? Right. We'll go into a little bit of a mathematical thing in a second on that, but conceptually, let's look at gravity field again. We'll often go back to gravitational field because, again, that's a little bit more within our realm of experience than electric fields, and generally the same analysis applies. All right. I weigh 150 pounds. When I experience Earth's gravitational field, I'm experiencing a gravitational field of 9.81 meters per second squared, right? My father weighs 190 pounds. When he experiences Earth's gravitational field, what's the value of the field that he experiences? 9.81 meters per second squared, right? Because he's heavier than I am, he doesn't change the Earth's gravitational field. It's dependent on the producer. He experiences it, the field caused by the Earth, but he doesn't affect what its value is. Nor does the charge that experiences an electric field affect the value of the field. So, why doesn't that mathematically work? Okay, we should be able to make mathematics agree with the conceptual analysis. What's wrong with what we've just done? John? Say it again. Okay, so I use the experiencer equation, but why is that wrong? Why is that wrong? I mean, I've got information about the experiencer there, and clearly it doesn't work. Clearly it's wrong. Why doesn't it work? What's wrong with what I did? I mean, I could go and try another equation, sure, but why can't I use this equation? We're not changing the producer? Okay, but still, like the producer doesn't even appear there, right? So it looks like a valid equation, and in fact, I'll tell you that it is a valid equation for this, but it just didn't give me the right answer for some reason. I've missed something here. Jack? Yeah, if you ended up using, saying F is equal to KQ1 Q2 over R squared, calculating the force, you would find that the force was half the value as well. I mean, think about that. The force of gravity, the acceleration due to gravity, or the gravitational field strength on my father is the same as the gravitational field strength experienced by me. But the force experienced by him is more, right? So, although his mass, if we were using G is equal to F over M for gravitational field, his mass went up by a factor of about, I don't know, 40%. So did the force go up by a factor of about 40%. If the charge was cut in half here, well, then the force on that charge would also be cut in half. That make sense? Well, then all of a sudden, a half divided by half is, and we're left with the new field is equal to the old field. Does that make sense? That's a tough question. That's a tough question. Anybody besides Rucker get that? Good. Good. You get the same? Good. Well, yeah, F is equal to Q times E, but you got to be careful with that, right? You can't, Rucker, you can't solve for force using Q times E and then turn around and plug that into this, right? Because everything ends up canceling out. Basically, you get 1 equals 1. So if you would actually find the force there, you'd have to find it in a different way using just Rucker, let me finish. You'd have to finish it using, or sorry, solve for force using K, Q1, Q2 over R squared, which, I mean, I wouldn't go that far and do that. Okay? But if you were to do that, you would find that the force would end up being half, right? In the end, one of the charges is half what it was, all right? Well, it's 1/2, Q1, Q2. So what does it become? 1/2 of the original force. Well, the charge was already 1/2. The force is 1/2. The halves cancel there. Okay. Mathematically, that might not be the simplest way to do it. I think conceptually it is a little bit easier if we just take a step back and say, wait, the experiencer doesn't affect the field. It just experiences it. Right? My father experiences the same gravity field as I experience. Not the same force, but the same field. Now, Rucker, what were you saying there? Right. No, but that's why I told you not to write that down because that was wrong. But I understood that was wrong, and that's essentially what I was trying to tell you. When look, don't write this down. I'm doing something that everybody's probably, or most people are probably going to want to try to do, but don't write it down because it's not right. Let's wait until we get the right answer to write it down. All right. So the field doesn't change. Next question, 8. Eight says a small test sphere with a negative charge of 2.50. Here we are. Remember yesterday I said your textbook likes to use the exponents, the scientific notation, but your exams like to use microcoulombs, nanocoulombs, whatever. Okay. Here we are with microcoulombs. We've got to circle that because we don't want to make a mistake and forget to convert that. Experience is a force of that value, and it's this far away from another larger charged sphere. What's the magnitude and direction of the field at this point, and what's the sign, the magnitude and the sign of the larger charged sphere? Let's draw a picture for this, okay? We got a bunch going on here. We've got a small test sphere with a negative charge of 2.50 times 10 to the minus 6 coulombs. It experiences a force of 5.10 times 10 to the negative 2 newtons. Now, it's a certain distance from another bigger sphere. Let's find the field at that point. Hey, let's look at the blue one and the green one. One of them is a producer, one of them is an experiencer. Which one's which? Which one's producer, which one's experiencer? Good. Blue one is the experiencer. Hey, we want to find the field strength experienced at this point. Hey, if we could find the field strength produced at this point by the green one, it'd be the same value. But we know nothing about the producer right now other than where it is. So let's use the experiencer equation for A. E is equal to F over Q, which is 5.1 times 10 to the negative 2 newtons divided by 2.5 times 10 to the minus 6 coulombs. Remember, we're dropping the sign of the charge there. What do we get when we divide those two numbers? 2.04 times 10 to the 4. And Katie, what would the units for that be? Good, newtons per coulomb. Oh, wait, we want to find the direction. We want to find the direction. Oh, it's an attractive force. So we know that the force is pointing this way. If the force on a negative charge is to the left, then the field must point to the right. Remember, positives experience a force in the direction of the field. Negatives experience a force opposite to the direction of the field. You guys remember that? That makes sense? All right, what about the magnitude and the sign of the charge? Well, if the field points to the right, we know what the sign of that charge is right now. What is it, Cassie? Positive, because the field points away from a positive producer, right? All right, the magnitude and the sign of the charge, the magnitude of the charge. Well, the only way we're going to find the magnitude of the charge is to use the producer equation. And look, we know the value of the field. We just calculated it. The field experienced, the gravitational field experienced by my father is the gravitational field that's produced by the Earth. The electric field experienced by this blue charge is the electric field produced by this green charge. So we're going to plug that value in there. I turn around and solve for Q here. It becomes E times R squared over K equals Q. We got the value of E, we got the value of R, don't forget to square it, and we get the value of K. We solve for Q there. I'm not sure what we get, but it's mathematically pretty straightforward at this point. Is that okay? Okay, let's take a look at number 9 now. Last one. A negative charge of 3, oh, here we go, another one, millicoulombs. Careful. Okay, we're used to seeing 10 to the minus 6 coulombs often, and then sometimes we see the microcoulombs, which is still 10 to the minus 6. This isn't, right? This is milli. It's 10 to the minus 3. It's 1.2 meters to the right of another one that's 2 millicoulombs. What's the field at a point midway between? And then what's, oh, we've seen one like that before, haven't we? For force, right? That's kind of the ugly one. Let's do A first. Draw it out here. We got charge 2, we'll call it negative 3.00 times 10 to the minus 3 coulombs. We got another one that's it's negative as well, call it charge 1. And then we got a distance between them of 1.20 meters. We're going to find the field strength midway between them, right here. So is there something to experience that field there midway between? I don't know. Maybe there is, maybe there isn't. If there is, we don't know anything about it, so we have to assume that there isn't. Let's look at the field caused by number 1 at that point, point X. The field caused by number 1 is to the left. And the reason it's to the left is because fields point toward negative producers. It's pointing toward charge 1, the negative producer. The field caused by number 2 is to the right. The reason is because the fields caused by negative producers are toward negative producers. It's going to point toward the right. We're going to get the value of both of those fields now. Anybody have the value of that for E1? Uh-oh, what did I do wrong? I made a mistake here. Didn't do it on purpose, but I just caught it at least. What's my mistake, Maddie? Good. My R value should be 0.6, right? Anybody have the value of that? Now that I have the correct number in there. Four by 99 times 10 to the 7 newtons per coulomb. All right. I'm going to do the lightning fast calculation in my head for E2. Show you how smart I am. 8.99, watch this. In my head, 8.99 times 10 to the 9 times 3 times 10 to the minus 3 divided by 0.6 squared is, I'm going to say 7.5 times 10 to the 7. I'm rounding. 7.48. Guys, how did I do that? Oh, so you're just estimating. Oh, so do it on your calculator and see what it is. Who's got it? 7.49, all right. We'll split the difference there, Rucker. How did I do that, by the way, guys? Yeah. Yeah, that's all I did, right? I didn't multiply these numbers together in my head. I just said, oh, what's this number? 5 times 10 to the 7, and then charge 2 is 1.5 times as much, so the field's got to be 1.5 times 5, which is 7.5, right? Okay, you get something like that. There's always a trick, right? Always a trick. All right, add these up now, guys. We got the net field is 4.99 times 10 to the 7 to the right, plus negative 7.49 times 10 to the 7 to the left. What does that equal? About 2.5? Negative 2.5 times 10 to the 7 newtons per coulomb, or 2.5 times 10 to the 7 newtons per coulomb to the left. Good? Okay, let's take a look at at 9b now. Here we have our two charges again, our -2 millicoulombs, and we've got our -3 millicoulombs, and we've got our distance of 1.20 meters apart. We want to find the point where the field strength is 0. Hey, closer to 1 or closer to 2? The charge is going to be closer to 1 or sorry, is that point going to be closer to 1 or closer to 2? Closer to 1. Well, closer to 1. How much closer? Not sure, but it's going to be closer to 1. And we know that because in the end, charge 1 has a smaller charge, same distance, it's going to produce a smaller field. Well, we needed to produce the same field, so we needed to be closer to that charge, smaller r. All right, let's define this distance as r, and let's define this distance, same as we did in that other question that we saw here a couple weeks ago, as 1.2 minus r. We know the field towards number 1, and we know the field is towards number 2. And we know that the field caused by number 1, at least the magnitude of it, must be equal to the field caused by number 2. KQ over r squared, KQ2 over r squared. Oh, wait, this isn't r squared. This is going to be 1.2 minus r squared. K's cancel. Q1 is 2, Q2 is 3. Hey, why did I do that? Why did I drop the 10 to the minus 3? We saw this in that other question that we did with forces as well a couple weeks ago. Why did I drop the 10 to the minus 3? Right. Since 10 to the minus 3 appears in both sides, it would just cancel anyways, right? In fact, what I even thought about doing was calling this 1. And this 1.5. Could I have done that? Same thing, right? I think that might be a little bit more confusing, so that's why I, in the end, decided to leave it as 2 and 3. Okay, let's do some rearranging here to solve for r. We'll pick it up here after our little crash here. We had 2 over r squared equals 3 over 1.2 minus r squared. We want to rearrange this to solve for r. Take the 1.2 minus r squared up by multiplying. Take the r squared up by multiplying. What can I do at this point? What could I have done at the last stage? Yep. Square root it. I didn't square root it at that stage. I can easily square root it at this stage, though, and it gives me the same thing. Square root of 1.2, sorry, of 2 is, I believe, is 1.41. Square root of 3 is you've got a couple of options here now. You can multiply 1.41 throughout there, or you can just take it over by dividing. Either one of those way works. What's 1.73 over 1.41? And now we want to take the negative r over by adding. So it becomes 2.2269r. And then we're going to say 1.2 divided by 2.22 gives me, I don't know, 0.6 or something like that. 0.5389 meters. So 0.5389 meters to the right of the first charge. Or really we should say 0.534 meters, right? That make sense? Tough question, right? Easier than the last time we saw something like this, though, I think. Because we've seen it before. Okay, I'd be surprised if we see something like that on a test or an exam. But you never know. Hey, we go through this, it makes us smarter, so we can answer the other ones a little bit easier.